Hello, everybody, and welcome back. So, today we are going to be continuing to talk about the idea of an integral and its relationship to sums and physical quantities that can be calculated using sums and using integrals. And I want to emphasize that today, what we're really trying to do is explore the thought processes that come up in this class, often the ideas that come up in this class, often the intention is not for you to memorize an algorithm, memorize a formula. The intention is for you to sort of conceptually understand where the principles of calculus are coming from. Now, previous episode, we saw that an integral is a sum, and in particular, it's a sum where the amount of recorded data that you're using is really large, or put another way, a sum where the gaps between your data points are extremely small, resulting in very accurate calculations and estimates. We saw in the previous episode that distance traveled was an example of an integral. You can integrate speed with respect to time and get distance traveled. Put another way, you can do a sum involving speed and time and get from that sum distance traveled. We also saw that mass was another example of an integral of density with respect to length. Put another way, you can set up a sum involving density and length, and that sum, if you use a lot of data points, give you a very accurate estimate of an object's density. What we're going to do today is we're going to explore a couple of additional examples of quantities like distance traveled, quantities like mass. We're going to explore additional examples of quantities that are integrals that can be calculated using sums and can be calculated very accurately using a sum that involves a lot of data. So join me on the following examples, and as we explore these examples, remember this is about ideas, this is about thought processes, this isn't about memorizing a specific process. So scenario number one, in the category of exploring volume as an integral, we have a selenite crystal. These things are super cool. I love crystals in general because they create these incredible geometric shapes. We have a selenite crystal, and let's say it's 8 centimeters long. And if you slice the selenite crystal along its length, then for this particular crystal, let's say that we get cross sections that look like triangles. So here's like a real life selenite crystal, and here's a sort of geometric abstraction of a selenite crystal, which is just triangles that have been stretched out along a line to create the crystal shape. Now let us suppose that no matter where you cut this crystal, no matter where you slice it, the triangles that you get from that slice all have exactly the same area. Let's suppose that all these triangles have an equal area of 4 cubic centimeters. If this is true, how would we calculate the volume of the entire crystal? Well, some of you may guess, some of you may know that if you have a shape that looks like this, a single area that's sort of just been stretched out along a line, then you can find the volume of this shape simply by taking the area and multiplying it by the length of the object. Volume is equal to the cross-sectional area times the length of the object. It's kind of like when you have the volume of a rectangle, you're basically just taking the area of the square base, length times width, and then multiplying it by the height as that base sort of gets stretched out. This is a similar idea, except that instead of dealing with a rectangular shaped base that's gotten stretched out along a height, here we've got a triangle shaped base that's stretched out along a length. In this particular example, if the cross-sectional area, if the area of each triangular sort of slice of this crystal is 4 cubic centimeters, and if the length of the crystal is said to be 8 centimeters, then just by multiplying the area and the length together, we get a total volume of 32 cubic centimeters. So this would be the length excuse me, this would be the volume of the selenite crystal in this example. Now, selenite's really unique, but in addition to selenite, there are all kinds of other crystals that have more irregular shapes, right? Like this one over here on the right side, I think might be quartz. It looks so cool. Now, unlike the selenite crystal, if I slice this quartz, then depending on where I slice the quartz, I'm getting different areas. Here, sort of in the middle of the quartz, this quartz would have like a big area somewhere here in the middle. Maybe the quartz would have a slightly smaller area if I did a slice here toward this little dent at the top of the crystal. Here toward the bottom of the crystal, it's sort of tapering off. So this would have a nice small area as well. So this is an example of a shape that has a non-constant cross-sectional area. So do you see the parallel to what we were doing yesterday? Yesterday we had an object moving at a constant speed, and then we transitioned to a non-constant speed. Yesterday we had an object with a constant density, and then we transitioned to a non-constant density. Here we have an object with a constant cross-sectional area, and now we're transitioning to an object that has a variation in its cross-sectional area. And the question is, in a situation like this, how could we calculate the volume? Well, once again, we can at least estimate the volume using the same idea, using the same sort of trick, the same assumptions that we used yesterday. If, for example, the cross-sectional area is given to us by this table, maybe the crystal is 6 centimeters high. We record the area at the base, and the area at the base is 4.7 cubic squared centimeters. Maybe if I move 1 centimeter up and record the area there, the area 1 centimeter from the base is a little bit larger, 6.1. I go up, I record the cross-sectional area a little bit higher along the crystal. Cross-sectional area is 5.1, and so on and so forth. If I have this table recording the cross-sectional area at these sort of different levels along the crystal, what could I do to estimate the crystal's total volume? The same idea from yesterday would suggest that the trick that we're going to use is to basically assume constant area on different chunks or pieces of the crystal. And as we saw yesterday, there are lots of different assumptions that can be made. One student may decide that they're going to treat the crystal as if it had a constant area of 4.7 between position 0, the base of the crystal, and 1 centimeter up. Another student may decide that they're going to treat the crystal as if it had a constant area of 6.1 between those two positions. Another student may decide to pretend that the crystal has a constant area somewhere between these two values, maybe the average of these two values. Any one of those is a valid approach. Once again, I'll give you simply one possible approach. One possible approach maybe I will decide in this example, just for some variety for the ones that we did yesterday, I'll decide to take the left value for each of these intervals. So I could say, for example, I'll assume that the cross-sectional area of the crystal is constant at 4.7 between position 0, the base of the crystal, and position 1 unit up along the crystal. If I make that assumption, the corresponding estimate for the volume of that chunk would be 4.7, the area, times the length of the chunk, which between 0 and 1 units would be 1 unit. That would be the volume of the bottommost chunk of this crystal based on this assumption. And then I would have to repeat the process to estimate the volumes of all the other chunks, the other portions of this crystal. So let me go ahead and do that off screen. I, for example, have decided I'm going to assume that this chunk of crystal has a constant cross-sectional area between position 1 and position 2. And I'm going to assume that the cross-sectional area for that chunk of crystal is given by this sort of left-hand value, this 6.1. And if this is the area, and the length of the chunk is between 1 and 2 centimeters, then the length of the chunk is 1 centimeter. So the volume of that piece would be 6.1 times 1, or 6.1 cubic centimeters for the volume of that chunk. Similarly, I could go ahead and assume that the chunk of crystal between positions 2 and 3 has a constant cross-sectional area of 5.1, this left-hand value. And if I make that decision, then the area of that chunk 5.1 times the length of that chunk, 1 unit, would be 5.1 cubic centimeters, and so on and so forth, right? So now with this calculation and with these 5 calculations, I have 6 different volumes for 6 different chunks of this crystal. And to find the total volume, all I would have to do is add those values together. And I emphasize that this is an estimate, and I emphasize that this is probably a pretty bad estimate, right? It's probably a pretty bad estimate because the assumption that we made that the chunk has constant cross-sectional area, this is a crazy assumption to make because we can see in the picture that this crystal doesn't have constant cross-sectional areas. But do you remember from yesterday's talk, one of the ways that we might improve this estimate, one of the ways that we might make this calculation more accurate and closer to the crystal's actual volume? You may recall that one of the best ways to make the estimate better is to collect more data about your crystal, to collect more measurements. Don't just measure the cross-sectional area every centimeter, maybe measure the cross-sectional area every millimeter. Increase the number of data points, decrease the space between the data points. The more data that you have and the more data that you're working with, the better your estimate will become. And as you use more and more data, your sum transitions into what we call an integral. Let's continue to explore this idea of using sums and using integrals to calculate volumes. And we're going to change the game a little bit here. In this case, our areas are not going to be given to us by a table. Our areas are going to be given to us by way of a function. So in scenario number 3, as we explore the idea of volume as an integral, suppose that you have a pyramid, and we're told that this pyramid is 7 centimeters high, 7 cm high in total. This is one of those pyramids that'll give you square-shaped cross sections. So I slice into the pyramid like this, and I get a cross section that's shaped like a square. And someone says, listen, there is a function that tells you the area of this square depending on where you made the cut. If you make the cut into the pyramid X centimeters from the pyramid's base, if you go X centimeters up, and you slice sideways into the pyramid at that height, the area of the slice that you get can be calculated from the height using the following formula. You take 30 and then you subtract 30 divided by 7 times your height. And if you use this formula, it'll tell you the area of each little slice. So now let's think. If I were given this information instead of this table, do you have any ideas about how you might get started estimating the total volume, not of the crystal, but of this pyramid? In this situation, there's nothing stopping you from making your own table. If you make your own table of the area of the pyramid slices at various positions, if you make your own table, then this problem reverts right back to the problem that we had in scenario 2. So let's go ahead and make a table of areas at various positions and turn this problem with the function back into this older problem with the table. So for example, at the base of the pyramid, where the value of x is equal to 0, because we have not arisen any centimeters from the base, if I plug 0 into my area function, if I plug in x equals 0, then the result of that calculation says that the area at the base of the pyramid is going to be 30 units when the position is 0, from 30 minus 30 over 7 times x equals 0. So I can plug that value into my table. When the position is 30, excuse me, when the position is 0, the cross-sectional area is 30 units. Now, as we continue to fill out this table, we realize right away that we have a decision to make. We have a decision to make about how many data points we want to use to fill this table in, right? Maybe we want to do exactly the same thing that this person in scenario 1 has done. Maybe we want to record the areas at, these integer positions, 0, 1, 2, 3, 4, 5, so on. And then we could plug in x equals 1 to this function, x equals 2 to this function, x equals 3 to this function to get the various areas, right? I've gone ahead and done those calculations off screen, and if you plugged in x equals 1, a position of 2, a position of 3, 4, 5, 6, 7 into this area function, then here are the areas of the square-shaped cross-sections at those respective heights. And you can see that at the very top of the pyramid, when the position is 7 units exactly, we get a cross-sectional area of 0. Now, for sure, if you decide to create a table that looks like this and use the same process that we used in scenario 2, that is a way to get an estimate for the volume of the pyramid, no problem. But as we have observed, using such a small number of data points creates a really bad approximation for the actual volume of the pyramid. But if we have the time to spare and we need additional accuracy, there's absolutely nothing stopping us from getting a table that contains more data inside of it. I could very easily go ahead and decide to measure the area at additional positions. Because I have the function that predicts the area of the pyramid at any height, I can create whatever table I want to. I can decide how much data I want to generate. I can decide how much space I want to have between the data points. When I am given a function that predicts the area instead of being given a table, I can make my own decisions about how much accuracy I want to achieve. Now, there are pros and cons to each of these options. Option number one is relatively fast. It requires us to do a relatively small number of calculations. By contrast, if I tune up the number of data points, if I increase the number of measurements of the pyramid's area, then I'm getting a calculation that's more accurate to the pyramid's true volume. But the cost of that is that it has increased the workload quite a bit. If I wanted my table to have more data in it, then I would have to plug more values of x into my area function. And when I finally actually got to the volume estimate, I would have more volumes of more chunks that I would have to calculate, and then I would have to have more volumes that I would have to add together to get the total. So in questions like these, where you have lots and lots of options at your disposal, where you have a lot of freedom in terms of how you answer the question, you have to make your own decisions based on the pros and cons on the table. Now, again, sort of toward the kind of problem in today's problem set, I want to add an extra little bit of complexity to a question like this one. So same scenario, same pyramid. Still 7 centimeters high, still has square-shaped cross sections. So far everything is very, very similar to what we had in the previous exercise. But there's one big difference in terms of the data that we are provided. In the previous example, we were told that if you slice the pyramid at a height of x, that your area is predicted by this function here on the right-hand side, 30 minus 30 over 7. But in this situation, the information that we're told about the pyramid is not the cross-sectional area, but the cross-sectional side length. Go at a height of x centimeters from the base, and I make a slice at a height of x centimeters from the base. What this function is saying is that that side of that slice, not the whole area, just this piece here on the side, that side length is predicted by the function 7 minus 7 over 10 times x. The question is, in a scenario like this one, how would you approach estimating the pyramid's volume? Now it remains true, right? That volume is equal to area times the length of that area. So if we could figure out some way to get the area of these slices from the information provided, then we would be able to fill in the area and basically revert this question back to the one in scenario number 3. If I can find the area, if I can find the area of these slices, then I can approach this exactly the same way we approached scenario 3. The question is just based on the information provided, what is the area? And to answer that question, the key bit of information is that these cross sections are shaped like squares. So if you have a square with a side length of 10 minus 10 over 7x, how from that side length do you find the area of a square? We square the side length to find an area of the square. Side length, this function of x, times itself, giving you quantity squared. Now that we have the function that predicts the area of these cross sections at various heights, now that we have this function, this is once again a scenario 3 problem. So let me just type out what would come next. What would come next after this step is basically it reverts back to scenario 3. We would have to create our own table of the area of the pyramid at various values of x. Once you have created your own table, it reverts back to a scenario 3 problem. Assume that the area of the pyramid is constant between the data points in the table. Then go ahead and find the volume of the different pyramid chunks and sum. Here we have the keyword sum to find the total volume. So to summarize, volume can be obtained by way of an integral calculation. In the language of this class, we would say that volume is an integral of area with respect to length, because we can calculate volume by using a sum that involves areas and lengths, and that calculation becomes more accurate as we have more data. Now, if you're given the data at the start of the problem, then that's all that you have to work with. But potentially you're in a situation where you have to create your own data, create your own table. And in situations like that, you have to make a decision. How much information are you going to include in the table? Are you going to include a lot of information that's going to give you a really accurate result? That's great, but the cost of that is it's a lot of work. It's a lot of work to make the table. It's a lot of work to do the calculations. Or do you want to make a table that's really sparse so you can get the problem done quickly at the cost of having probably a really bad estimate for the volume? Volume is an example of an integral. Volume is the integral of area with respect to length. The second half of this video is just another exploration of another scenario where this idea shows up. Here we're going to talk about arc length as an integral, arc length as a sum. So scenario 1, we have an object traveling along a straight line path at the point, say, -1, 1, and a point, say, over here at coordinates 2, 5. Question is, if the object travels along this straight line path, how far did it go? Well, we have a formula in mathematics that tells us the distance between 2 points, the length of a line segment between 2 locations like this one. We have the distance formula. And that distance formula says that the distance is equal to the square root of the difference between the 2 horizontal positions and the 2 vertical positions. So in this case, we're dealing with the square root of 3 squared and 4 squared, so result 5 units. Now we have that distance formula in the situation where the object is traveling in a straight line directly from one position to another. But then one could ask, what happens if the situation's more complicated than that? What happens if your object is traveling along a path that potentially is curved? It's not straight. In a situation like this one, how would I get a sense, how would I get an estimate of how far this object traveled? Well, once again, we're going to use the same idea that has shown up in all the examples so far. We're going to take this complicated problem, this difficult problem of finding the length of this curved path, and we're going to make some simplifying assumptions to make the calculation possible. So one assumption that we could make to make the calculation possible is to say, I'm going to assume that instead of actually traveling along a curved path, the object traveled along a sequence of straight line paths. Hopefully this drawing is clear. I'm trying to get used to a new drawing tablet, and it's messing me up. Why am I making this assumption, do you think? How does this relate to the ideas that we've explored up to this point? Well, I'm going to make this assumption because it is possible for me to use the distance formula to find the length of each of these straight line paths. And then I can add together, I can sum these individual lengths, and that sum of these individual lengths of these line segments will give me an estimate for the total length of the path. So for example, if someone recorded that the object's horizontal coordinate and vertical coordinate at these various times were given to me by these data points here, xy coordinate, xy coordinate, xy coordinate, and so on. Let's explore what it would look like to answer this question using this idea. If I make this assumption, if I use this idea, then the length of the first linear line segment could be found by using the distance formula as applied to the horizontal coordinates and the vertical coordinates at the start and at the end of that first line segment. Now we're told that the horizontal coordinates between the beginning and end of that first piece are 4 and 0. So if I plug those two in, I get 4 minus 0 quantity squared. And the two vertical positions, the two y coordinates between these first two endpoints here, we're told are 0 and 2. So I can add those together, 2 minus 0 squared. And in that case, we get a distance that's approximately equal to 4.5 units. That would be the length of this first linear line segment. The length of the second line segment could also be found using the distance formula. I'm told that the horizontal coordinates of the left and right side of the second line segment are 4 and 8. So I could plug 4 and 8 into the distance formula. And I'm told that the vertical coordinates of the left and right endpoints are 2 and 1. So I could plug 2 and 1 into the distance formula. And as a decimal, this distance is approximately equal to 4.1. Using similar assumptions and similar calculations, I can use the data in the table to calculate the lengths of any additional segments along this curved path. So let me do that off screen. And now that I've found the length of each of these individual line segments, the total length of the curve would be approximately equal to the total length, the combined length of each of these line segments. So whatever is 4.5 plus 4.1 plus 5.0 plus 2.8, this would be an estimate for the length of this curved path. But again, visually we can see that approximating this path by 4, 5, 6 line segments is not going to give you a very good estimate for what the path is actually doing. So again, any ideas for how we might be able to improve the accuracy of this calculation? Once again, the accuracy can be improved simply by increasing the amount of data that you use in your estimate. If you use a large amount of data, then the line segments that you are using to estimate the curve become really small. You put very small amounts of space between your data points, then the line segments hug closer to the curve, and the line segments become a better estimate for what the curve is doing. So once again, we see this same theme. Now, if you have been given a table of data that someone else has made, then you're limited by what choices they have made, right? If they only give you a small number of data points, then that's what you're stuck with, and you're limited in how much accuracy you can achieve. However, just like in the volume example, if you are given not a table, but if you're given a pair of functions that predicts the horizontal coordinate and the vertical coordinate at various times, then you can make your own choices about how much data to generate using those functions. You can make your own choices and say, I want a really accurate calculation, so I'm going to use these functions to make a really big table with a lot of information in it. Or I don't really care about accuracy, I just need speed. So I'm going to make a table that has very little information in it. It's going to be a bad estimate resulting from something like that, but I don't care. I just want it done fast. The advantage of having a function is that it leaves that choice up to you as the student, as the mathematician. That choice is not made for you. So that concludes today's video. Yesterday we talked about mass as an integral, distance traveled as an integral, but there are a lot more physical quantities that can be calculated or estimated using sums. And therefore, using integrals, because an integral is just a sum that involves a lot of data points and is very accurate. For example, today we saw that volume can be thought of as an integral involving area, and the length of a curved path, the length of an arc, can also be obtained by summing up tiny lengths of line segments that are used to estimate the curved path. We also observed that, it's great to be given a table of data for your sum, but it's even better to be given the information using functions. Because if you're given the information using functions, then you can create your own table and you can make your own decisions about how much data you record and how accurate you want your calculations to be.